So hi, welcome back to day 2 of the PhysiCell virtual workshop and hackathon. We are going to pick up on what we already started doing yesterday and start learning about functions in PhysiCell. And these are going to be for the purpose of taking the intermediate workflow we started with yesterday and adding on dynamical functions that can modulate cell behaviors based upon what they see in their environment. So the code for today's session is available here at GitHub, and so you can browse through, go to the agenda materials, go to session 6, and you'll see a link for all of the code for today. So our goals for today, for this session, is to introduce now the full modeling workflow. We want to show you the typical syntax, form, and purpose of the PhysiCell functions that you can attach to cell agents, and learn about what possible functions can be attached to cells, and learn how to assign new functions to a cell definition. And then after that, we're going to go through an example. We're going to take a basic tumor growth model, and we're going to make cell birth and death based upon oxygen. And then we're going to have dead cells release debris. And then we're going to introduce macrophages that consume debris and chemotax towards it and phagocytose dead cells. So we're going to get to a fairly good working tumor macrophage example by the end of the session. The stretch goal here, and I want to make sure I'm mindful of the time, but the stretch goal is then if we can also do some work on controlling the initial placement of cells and introduce custom coloring functions to control what those cells look like. Okay, so let's go ahead and continue through this. So the full modeling workflow is an extension of what you saw yesterday in the intermediate workflow. You know, like any good mathematical modeling, you should start by planning. Before you write a single line of code, you should be planning. So plan on a project. Then we're going to populate the template project. We're going to edit the domain, microenvironment, and cell definitions in the graphical model builder, add custom variables and parameters. So anything that's new from in the full workflows here in red. Now that we are writing C++ rules, we can make use of custom variables and parameters in our functions. Then we're going to start editing the custom code. We're going to declare functions, implement them, and assign them to the cell definitions. And then optionally, you'll edit cell placement, the coloring functions, then recompile, run, and have some fun. So reminder, about the structure of a PhysiCell project. Remember that if you look into custom.h, this is where we really declare a lot of the functions that make a project work. And a lot of them are already kind of built in and kind of filled in as a template for you to add and modify. And so there are setup functions, cell definitions are going to be defined here, custom functions will be defined in your header file, and any other custom coloring functions. And if you start browsing through custom.cpp in particular, you'll start seeing that there are a variety of functions that we're going to be making use of. One of the most important ones is create cell types. This is where we're going to adjust the kind of the initial properties of the cells definitions and assign functions. Set up tissues where you modify the placement of initial placement of cells. And if you want to modulate their initial, say, cell cycle status, for example, that came up yesterday, that would be the place to do it. And then any other custom functions get modified in the custom, in this custom file. So the main structure of the project, you open up main.cpp and there will be a function called setup microenvironment. This will parse all the XML and set up all your diffusible substrates. Thankfully, we don't have to worry too much about that anymore. And it calls all the setup functions. So it's really like a humongous script when you get down to it, a choreography really of functions to ensure proper initialization. And then creating cell types is going to run. So that's going to run anything you put in there, including kind of the default code. Then setup tissue is going to place your cells. Here in main.cpp, there is a function called cell coloring function. It's a function pointer, actually. And so if you make your own custom coloring function, this would be where you assign it. And then in the main loop, it kind of goes through and we'll do things like decide if it's time to save, update the microenvironment over here, update all the cells according to all the functions that are hidden in there. And then there's kind of a space before the end of the main loop. And if you had some kind of a custom plugin that you wanted to do that's kind of beyond the basic built-in processes, that would be a good place to put it. So where things go, custom functions are declared in custom modules custom.h. You implement those functions in custom modules custom.cpp. You assign your custom functions in the create cell types function, and you define any custom data and parameters in the XML configuration file, now using the graphical model builder. And so let me give you a bit of an overview of what functions look like in PhysiCell. They almost all have the exact same form, and we want to make this so as easy as possible to have kind of a consistent convention, so you can kind of transfer functions around. But they'll all have pass a cell pointer as a first argument, the cell phenotype by reference in the second argument. This really is not necessary, but it can be convenient for acting on the cells, a little bit less typing. And then double delta T is how far you're going to advance your intracellular model or your function. And the functions can access pretty much anything in the cell. You can get the cell state, things like the mechanics, pressure, neighbor list from PhysiCell-state, pointer state. You can access custom data using the dictionary. So you can do a get single cell behavior, put in the cell pointer, and then custom colon in the name of your variable, your custom data. Or you can set it, oops, there's actually a typo here. So I'll fix that now and update the slides later. Let's see here. But there's basically get and set, right? So you can set a single cell behavior saying which cell am I working on, the cell that just passed by pointer, custom colon, name of the custom data, and then the new value. You can access the functions by PhysiCell-functions. We'll get to that in a moment. You can also reference the cell phenotype used. So think to session 3 yesterday that was introduced by Anika and Furkan. You can get a single cell behavior by this function get single behavior cell and then the name of behavior like apoptosis, necrosis, a secretion rate. And what I'll do is I will make a PDF later that kind of has the template for the typical signal and behavior names. And then, of course, you can set a value, same thing, cell, behavior name, and the value of the parameter. And you can access your cell definition to get a reference value. So you may have your current cell proliferation rate in your single cell, but maybe you want to kind of resync it up to the reference value from your cell definition. Well, this is how you would access that value. You can also use easy functions to sample the microenvironment. So you can say get single signal, the cell, and then the name of the substrate. Get single cell signal, my intracellular substrate name, so my internalized value, or get single signal has my cell, and then maybe my substrate name gradient. So this could be get P-cell oxygen, P-cell intracellular oxygen, P-cell oxygen gradient, and that will give you the slope. So you can access a lot of information pretty easily now from the microenvironment using these libraries and these dictionaries. So there are a variety of functions that are possible to attach to cells, and they're all stored in that cells.function part. And they, like we mentioned a moment ago, they almost all have the syntax of a cell pointer, phenotype by reference, and a delta T to say how long to evaluate your function. And so the most important ones here, the ones that you'll be tending to work on are red. But there's a volume update function which uses right now a default model to remember the session 3, Anika's presentation, and Furkan's, where the cells could either grow or shrink towards their current target volume. So that is all based and built into this volume update function. So you could build your own volume update function if you wanted to. Update migration bias, right now, actually, you will almost never need to update this thing because the built-in chemotaxis and advanced chemotaxis will be able to do this. So probably not even red anymore. Custom cell rule has this form, and this is a function that will evaluate at every single mechanics time step. So it updates very, very frequently. Update phenotype updates at every phenotype time step, so much less frequently. And typically, that's the function we're going to be modulating. Update velocity is the built-in mechanics based upon the potential functions. Set orientation is right now not really something we want people to mess with. And then there's a contact function, which will allow two cells to interact with one another in a kind of an arbitrary way. And we'll spend more time on that in session 15, I think, for today. So all these functions, like we said, volume update is really what allows the cells to grow or shrink towards their target values. Update migration bias is how the cell chooses a new direction for migration during bias and random migration. Custom is just a catch-all where you can add pretty much anything you need to and do it fairly frequently. Update phenotype is the more general purpose one that will help change your phenotype parameters. And that's almost where you'll spend all of your modeling time. Update velocities, mechanics. Orientation is basically to choose the up direction for cell division. And note that in the 2D simulation, that had better always be up so that your daughter cells get placed along the XY plane. And then contact function is something we're going to do in session 15, not in session 7. And so really kind of like a really basic prototype here is you would have some kind of a phenotype function that you declare in your header file, say my phenotype function, but the same syntax. And then in your custom CPP, you're going to write your code. So here's an example where I'm going to get I'm going to get a custom parameter for my cell called rate. And then I'm going to set that rate to my cell's apoptosis. And actually, I think my capitalization is wrong on this. I think that's actually capital apoptosis, if I remember correctly. So let me fix that. And then, so I've declared a function, I've implemented it. Notice that I'm kind of referencing the cell pointer here. And I'm going to use the function to go into the setup create cell types function, and I'm going to add, say my cell defaults would use this function, for example, cell defaults.functions.update phenotype equals this function I just declared. Before I look at the questions, let me give you just a little bit of handy C++ that will help us to kind of navigate through some of this. And I think you already saw this in your session 5 overnight, but to recap, we can get a pointer to a cell definition very easily using the function called find cell definition and then type in the name of the cell type. So this would be a character string like cancer cell, fibroblast, or if you happen to know it's integer, which you probably won't, you could also find it by its definition. We'll also point out that there are built-in response functions in PhysiCell you can use in your cell functions. So a linear response function is this one on the left, and it will ramp, say, between negative infinity and S0, the value will be 0. Between S0 and S1, it will increase linearly from 0 to 1. Then when you're above S1, you just stay at 1. And so that's a nice function you can use for a linear response. We also have a decreasing linear response that basically does the same thing backwards. Starts at 1, decreases linearly from 1 over here to 0 at S0, and then 0 everywhere else. And we also have a built-in Hill response function. So this would be helpful for people thinking about therapeutics and pharmacodynamics. This is a function that starts off at 0 and then ramps up kind of in a nice slope towards 1. You reach half of your maximum at the half max value, and the steepness of the Hill response function is related to the Hill power. Kind of scales and linearly correlates with that slope. A couple of notes. We have built our Hill function so that if you give a negative value, it will just output 0. So it should be safe for negative values. Also, note that Hill functions can be very computationally expensive. And so a tip is if you have an integer Hill power like 1, 2, 3, or 4, it's going to be like at least an order of magnitude faster to evaluate than if you enter in something like a full floating point power like 1.307. So if you're kind of in doubt and you're calibrating and let's say your data assimilation and your model matching says that my Hill power ought to be 1.03, that 0.03 difference is probably not worth the performance hit. And I would personally recommend just using a Hill power of 1 in that case. So it would be much better performance. So I'm going to look at the questions now. And it looks like people are talking to each other on the voxel indices. And so that's great. So I will leave those questions be, and we can always discuss those more in the hackathon. So let me now introduce the full modeling workflow and give an example. So to make this concrete, we're going to do a very fixed model. We're going to start with 2 cell populations. Cancer cells will have a cycle entry proportional to local oxygenation, and necrotic death will have a probability that increases once you're below some threshold. And dead cells are going to release debris at a rate proportional to their volume. And we're going to use that debris to attract macrophage. So we'll chemotax towards debris and consume it. And if they encounter a dead cell, they will phagocytose that dead cell. Okay, so that's what we're going to do. So here's our full workflow again. We're going to start with the intermediate workflow. We're going to use the graphical model builder to make the domain, microenvironment definitions, and then add the custom variables and parameters we need as we need them after we're done planning our model. And then in C++, we're going to define these custom phenotype functions and update the coloring. Okay, so checklist, right? We're going to plan. We're going to iteratively add things in Model Builder, and then we're going to refine in C++. So let's kind of work through our checklist here. So first we want to edit our microenvironment. So I'm going to pick a much shorter simulation time of just a couple of days here, so we don't have to wait a long time as we iterate through this work. I'm going to reduce the domain a little bit to basically 800 microns by 800 microns. I'm going to have auction with default parameters, boundary initial conditions to, well, actually, I think I'm going to do probably not 38, but 15 millimeters partial pressure. And then I'm going to do debris with a much smaller diffusion coefficient and no decay and no flux. And I'm going to make sure the virtual walls are on so that cells don't leave the domain. And then I'm going to do custom data, as it turns out, that we're going to have proliferation and things like this. So we're going to have the response function, the thresholds. This is my S0 and S1 for proliferation. This is my S0 and S1 for my necrosis, and then max necrosis rate when you're in very low oxygen, and then the cell definitions. For the mathematics, so what I'm going to do is I'm going to just pick a really simple linear response curve using the simpler live cell cycle model. So my transition rate from phase 0 to phase 0, which is basically when I proliferate, is going to be scaling a maximum rate linearly by the difference in the thresholds. So, oxygen as it drops below let's see here. The oxygen, as long as it's above a threshold value, will increase the proliferation. If oxygen equals threshold value, we're at 1. If oxygen is at a threshold value, we're at 0. So you can see how those are my cap values here. And then necrosis will be the other way around. We'll do a decreasing linear function where once oxygen drops below a threshold, you'll start increasing the necrosis rate until you reach a saturation value where you have maximum necrosis. And so that's our planning. And based upon, so actually I would recommend doing kind of in reverse, plan out the mathematics of your model. That'll tell you what parameters you need as custom variables, and then you'll know what you need to do in the graphical model builder. So let's go ahead and get going. I'm going to go ahead and open up a command window, and I'm going to get ready to go with the first steps. I'm going to type make template. So I'm in a clean slate right now. Now I've brought in and populated all the files we need for the template project. Make once again to start compiling that. And so that's going. And actually, while it's building, I'm going to open up a second command window for my model builder. And so you're going to see a few variations here between different people. So you kind of see that there are lots of options. I'm going to type Python. And now in my directory structure, my graphical model builder is one directory level up in PhysiCell model builder bin Python model builder.py. I'm going to open up the studio edition here. So I'm going to make sure that you guys can see what I'm typing. And that's going to spin up Python and spin up the graphical model builder and give me a warning, which is a good idea. And so now we're ready to start. So I'm going to go here to File and Open. I'm going to go into my configuration file. So see I'm in my PhysiCell directory. I'm going to open up my settings file, just hit Open. And I'm going to hit Save again, just to make sure I'm really saving on this file. And now we're getting started here. So we've opened our configuration file. And now we're going to start editing the domain, kind of going through a checklist. So I want to pick my domain from -400 to 400 X and Y, and my max time to 2 days. And I'm going to save everything. Well, I have a contradiction between these two, either 30 or 60 minutes. It doesn't really matter, I guess. I'm going to save maybe a little bit more frequently. So -400 to 400 on X and Y. Z I'm going to leave alone. Reduce the maximum time to 2880. And I'm going to save my output every, let's say, 30 minutes, both the SVGs and these, the full data. And let's make sure that virtual walls are turned on with this checkbox. And now I'm ready to save. So I'm just going to save this once again. One thing that is not a bad idea is just to double check here. So I'm going to go into config, and I'm going to open up my PhysiCell config file in like my code editor, which is your Visual Studio Code. I'm just going to make sure these changes are really applying correctly, and it looks like they are. So I'm going to check that from time to time just to make sure things are going okay. And let's see here, where are we on our checklist? So we did our planning, we've set the domain. Now we need to start up setting up the diffusing substrates. So I'm going to go now back into my model builder, and I'm going to go to the microenvironment tab and start working on setting up my virtual environment. So first thing I need to do is to rename this default substrate to something more model specific to oxygen. So I double click this name, type oxygen, and hit enter. Now I've renamed it to oxygen. I'm going to reduce the decay rate to 0.1. This would give you a 1 millimeter diffusion length scale. And then let's set my initial condition to 15 and my Dirichlet condition to 15. So actually I'm going to modify probably my spreadsheet here. I'll pick it to 15 because I think that's just a nicer value to use. Okay, so I've done my oxygen so far, but I also need debris. So I'm going to go back into my model builder. I'm going to pick on this substrate here, oxygen, click copy. So now I have a second diffusing substrate, double click and rename it to debris. And I'm going to give it a much, much lower diffusion coefficient of 1. So basically it's barely moving with no decay, no initial condition, and no Dirichlet condition. I'm going to turn that off because that wouldn't make sense for debris. I'm going to set this to 0, but I have Dirichlet condition turned off for debris. So let's hit this to save. So now we're at a 0 flux condition for the debris. Okay, let's keep going through our checklist. We've set the domain, we've set up our diffusing substrates, the things in our environment, and now we're going to start adding our cancer cells. So let's see here. How to open the editor. Let me go. So Maria, if you download the slides, you'll be able to see that. So I want to just kind of remind people, if you go to the workshop 2022, click on the agenda materials, you'll be able to get the slides. So if we scroll down here to session 6, click this link and you'll be able to get the slides in case something passed by a little bit too fast. So going back just a few slides though, to make sure that you get that, the command I'm using to open the graphical model builder is within my PhysiCell directory. I'm typing Python, and then I installed it in one level up in PhysiCell model builder. So I do .. PhysiCell model builder bin. This is a mouthful to say, but this is my syntax. And I'll tell you what, I'll copy that syntax into the chat window here of the call. Hopefully that will facilitate things. Let's see, here's the chat window. So there's the syntax for that. And you should also be able to find that in the slide deck. Great, and if you can't keep up, don't worry. Let's call this a walkthrough, right? So what I encourage you to do is, once we're done with it, and then tonight when the recording is available, kind of go back through it and record it, pause as you need to go through these steps. You'll have the full code available. You'll have, of course, the slides for reference material and then the recording. So this can kind of act as a walkthrough. So this is like think of it as a guided tour as we build this project, but you can kind of see it in action. So these are really great questions. Thank you. So we have the substrate, the debris. Now it's time to make some cancer cells. So we're going to go back to the graphical model builder. Oh boy, that's almost confusing seeing these screenshots on top of this, but we're going to the graphical model builder and go to the cell types tab. And I'm going to click on this default type and double click it, and I'm going to rename it to cancer. So just double click it, type cancer, hit enter to take the name. I'm going to go to my cycle now, my cycle tab, which should be the default tab. And I'm going to pick a simpler model representation of live cells. And I find it easier to work in transition rates rather than duration. So I'm going to change this to transition rates. And let's see, we should pick a good transition rate for cancer cells. So I'm going to pick, it looks like 7.2 times 10 to the negative fourth. This is in minutes inverse. And so I'm just going to hit save now. But this says, well, let's see, if we go calculator, 1 divided by 7, 0, 1 divided by 0.00072 gives you a mean waiting time of about 1,400 minutes between cell divisions. Divide that by 60, gives you, in the ballpark of 23 to 24 hours for a cell cycle. Okay, so now let's go ahead and work on the death rate. So I'm going to click on the death, and I'm going to change the mean waiting time to become apoptotic to 7.2 E negative 5. So I'm just picking slightly simpler parameter values so that my death rate is about 1/10 of my maximum birth rate. So we'll have net proliferation here. And now let's set the uptake for cancer cells. So we're going to go here, we're going to skip these other tabs for a moment and go all the way to secretion. And I'm going to pick oxygen from the dropdown. And I'm going to make sure that cells are uptaking oxygen at a rate of 10. The reason I'm choosing this value is that when I take my square root of my diffusion coefficient by my uptake rate, that square root gives me a diffusion length scale and says that in densely packed tissues, we're going to have about a 100 micron diffusion length scale, which is about what you see in viable rims in cancer. So I'm going to hit save now after I've picked that uptake rate. Nothing else really needs to be changed on secretion. And now I'm going to go ahead and go to the custom data tab to start setting some of the parameters that I know I'm going to need for the C++ models later. So custom data, and I'm going to go and I'm going to double click sample. We don't really need a sample value. We need something more meaningful. So I'm going to do PO2, proliferation, saturation. Boy, copy pasting would probably be a little bit less risky. And I'm going to set my default value to 38 for this. This says that above 38 millimeters of partial pressure, or about 5% oxygenation, that I have maxed out my proliferation. And then I'm going to make another one called PO2 underscore proliferation threshold. This is the value above which we start proliferating, and they say right around 5. This is about when cells become pretty bad hypoxic. I'm going to make two more. I'm going to make one called PO2 necrosis threshold and set that value to 5, saying that when oxygen drops below 5 millimeters partial pressure, they're going to start getting pretty hypoxic. They're going to start becoming necrotic. And then PO2 necrosis saturation, I'm going to set that value at 2.5, saying that once I'm below 2.5 millimeters partial pressure, we reach our maximum amount of necrosis. And I'm going to set my max necrosis rate to be 2.8 e to the negative 3. This all comes from a reference paper, basically, original PhysiCell method paper, but it'll give you kind of how long cells can survive in extremely low oxygen conditions before they become necrotic, calibrated to a typical breast epithelial line. Okay, so we have set up the custom data. Let's just maybe double check that this looks right. Proliferation, saturation threshold, necrosis threshold and saturation, and max necrosis rate. Good. Okay, so we've got that. And then we could set, this would be maybe not a terrible time to test the model. So I'm going to go over here into the user parameters tab, and this number of cells says by default it will take 5 cells of each type and sprinkle them randomly in the environment. Let's increase that to 100 cells randomly placed in the environment. And hit save again, make sure it's overwriting the configuration file. And let's double check that all those changes I've taken, I'm seeing oxygen, I'm seeing debris with no boundary condition. I'm seeing a cancer cell type. These parameters look right to me. We have proliferation and death. We have, let's see, in secretion. We have cells up consuming oxygen. That's good. And then we have these custom variables that we just defined. So yeah. So now we're going to go ahead and run the model. Oops. I tricked myself. My screen cap looked too much like the real thing. So I'm going to go here to the Run tab, and this is an important step. I messed myself up this way too. The name of our executable is not template, it is project. So I'm going to type project in the name field here for the executable, and this config file is correct, so that looks fine. And since I've already compiled my project and I haven't made any custom C++ yet, I can go ahead and click just the Run Simulation button. So let's maybe save the file one more time, click on Run. And you should see basically the terminal output popping up right here. We can click on legend to see we have one cell type and it's gray, cancer. And if I click here on the first tab, I can see that I got my 100 cells randomly sprinkled. Looks like I have 102 for some reason, but you know, okay. Well, I've already gone 30 minutes, I guess. I'm going to click some substrates to visualize also the oxygen on top. And notice that the oxygen is actually quite low, which worries me a little. That maybe I don't have my boundary conditions turned on. So let's just hit play and watch this. Yeah, my oxygen is really, really low. And notice that my cell count, well, of course, we don't have any oxygen-based birth and deaths, so they're going to proliferate anyway. So I'm going to hit pause and just go back to microenvironment, make sure that oxygen, I'm going to uncheck and recheck that Dirichlet boundary condition and then save it again. And the run is just about done, so I can go visualize that one more time. I'm going to go into my parameter file and see what's up with that. It's funny, I do have my Dirichlet initial condition enabled at 15, so I don't know what's going on with that. So let's click on run again. And go back to plot, go to the original time. There we go. Now we see oxygen's 15 all the way around. Click on debris and it's nothing, which kind of what we expect. And as we play through, see that wherever there are cells, you know, they're consuming oxygen. And so you see these oxygen gradients are starting to emerge, which makes sense. So we're getting some cell proliferation. And again, we don't have any functions yet, so this is not like oxygen-dependent birth and death. So, you know, this is good. We went to the plot and we kind of looked through. We can kind of go to the very end and kind of click on more of these frames as they emerge. But it looks like we're in pretty good shape here. So let's continue. So in our checklist, we've built the domain, we have the diffusing substrates, we started adding the cancer cells and testing. And so, yeah, this is really great functionality, and we're so grateful to Randy for this. And we hope that it makes modeling a lot easier. Let's add macrophages. So we're going to go back into our graphical model builder. Let's see if I can find it. Here we are. Go back to cell types again. And I'm going to click on this cancer cell type. I'm going to click copy and double click it. And now I'm going to rename this to macrophage. And let's start setting the properties. I want some macrophages that don't cycle or die. So I'm going to go back to cycle. I'm going to set the transition rate to 0. And death, I'm going to set the apoptosis rate to 0 so that these cells neither born nor die. Let's just go ahead and save it as we're going. And I'm going to go and check my parameter file and make sure that's popping up. So I'm going to click on revert file and just make sure it really loaded. Okay, so I'm running into a bug that I ran into this morning where after I clicked the run button in the studio, it doesn't seem to be saving my information to the parameter file. It's like somehow not flushing to the cache. If I click on run, my model builder will see the new cell. Oh, well, now it popped. Clicking run seemed to flush it out okay. So I guess we'll keep going. So I've added a macrophage that doesn't really do anything yet. So we're not going to worry too much. We're going to let that keep running while we work here. But we went to here into cell types. We made a new macrophage. We turned off birth and death. And now we're going to adjust the mechanics a little bit. For macrophages, I don't think it makes sense for them to do cell adhesion. They are very motile. So we're going to set the cell adhesion strength to 0 and leave, and also I'm going to make them have a little bit larger of a sensing distance. So I'm going to set the relative maximum adhesion distance to 1.5. So they can stretch about 1.5 times the radius to interact with another cell type or to do their motility. So I'm going to give them that larger sensing distance and hit save. Okay, so now I have macrophages that are neither born nor die. They'll just be an initial fixed population, and they are not adherent to other cells, and they have a slightly larger deformation distance or sensing distance. And now I'm going to turn on chemotaxis. So here we go to the motility tab, and I'm going to click and make sure, first of all, to enable motility. I'm going to leave all these parameters alone. I'm going to leave actually the bias at 0.5 for now. But I'm going to enable motility, and I'm going to make sure they turn on chemotaxis. So click this enable checkbox here. And I want these cells to be chemotaxing towards cell debris. Now, there is no debris yet, but when it is, they'll be ready. So macrophages, motility on, chemotaxis enabled, and we have selected from the drop-down that they are going to go towards gradients of debris. So click Save. So far this is still mirroring, the intermediate workflow, but we'll be set up then for when we're ready. Now we're going to go to the secretion tab, and I'm going to say that macrophages should have, the same oxygen uptake. Let's just say that they consume oxygen too, but debris is interesting, that they should be consuming debris because they're kind of scooping it up. So we'll just set a very small uptake rate of 1 and click Save and leave that alone. We should be in good shape here. And then we're going to turn on phagocytosis. We'll go to the interaction tab, and we're going to set, that macrophages should be phagocytosing dead cells. We'll give them a rate of 0.01. So on they'll wait on the order of almost 2 hours before they phagocytose something. So hit Save. And let's see, we should be in pretty good shape. So now we've written all this. Let's go here to run. I'm going to click Save one more time, and then click on Run Simulation. And what we should be seeing here is now the second cell population, the macrophages, that should be wandering randomly because there are no debris gradients yet. Nothing's releasing debris until we write our rules for that. So click on Legend, you see the 2 cell types. I'm going to go back to the very beginning of the simulation. And so you can see the gray are the tumor cells, the red are the macrophages, and I can kind of advance through and see how the macrophages are wandering around kind of aimlessly right now. If they do happen to find a dead cell, they'll go ahead and phagocytose it though. So, oh yeah, see, he phagocytosed that guy right there. And so things are looking good. I think we're off to a good start. So we built the macrophages and tested. And now if you need to catch up to the code, unzip the checkpoint 1 code in your PhysiCell directory. So let me take a second just to look at the chat. It looks like people are having a really fun time here. So actually, I think I'm going to let this conversation go. So I'm glad to see you guys are having some good thoughts. So let's continue now in the checklist and start building the custom rules. And I'm going to double check my configuration file and make sure the macrophages are here. And I'm going to go down to motility and make sure that it really did write the debris chemotaxis, the uptake of debris, and that we have dead cell phagocytosis. So everything is looking pretty good here. So we're in good shape. So let's keep going through our checklist. So now it's time to start declaring our custom functions. In this particular model, the only cell type we need a custom function for is for the cancer cells. So we're going to go into, so actually I'm going to get out of full screen mode so I can just copy paste easily. I'm going to grab this code right here, and I'm going to go and go ahead and open, let's see here, go into my custom modules directory. I'm going to open up both the header and the source file. So let's go to the header file, just go down to the very bottom, and I'm going to declare my custom phenotype function for cancer cells. Make sure you save that. Okay. Now, okay, let's go ahead and hide the ribbon toolbar here if we can. Oh, that's not it. There we go. Just trying to hide some of this so it's a little bit bigger, but we can access the text easily. So I have declared my cancer phenotype function, and now I'm going to start implementing it. So what I like to do when I'm implementing a custom code is kind of outline what I'm going to do and then fill in the steps. So my cancer phenotype function is going to first check and see if my cell is dead, and if so, I'm going to set all my secretion uptake to 0 and manually set an export of debris. Then I'm going to sample my oxygen, and I'm going to set my birth rate and my necrotic death rate based upon my oxygen. So that's kind of the sketch of my model here. So I'm going to go into custom.cpp, go to the very end, and paste in this outline for my cancer cell phenotype function. And let's see here. So if we go to that, next slide, I'll start filling in this detail. So first I'm going to check to see if the cells are dead. So I'm going to use these dictionaries to figure that out. I'm going to have a Boolean variable called dead. I'm going to get the single signal from my cell, which is called dead, and see if they're dead. And then if they are dead, I'm going to get the volume of my cell, again, using the dictionary for the single signal. And then I'm going to set my cell behavior for oxygen uptake to 0. I'm going to set my single behavior for my debris export rate to be linearly proportional to my volume. I might as well just make that proportionality constant 1 for now. But this would be a great project down the road, actually, if someone wants to actually make something more mathematically robust and rigorous, right? To actually do conservation, say that we have the solid degradation rate for apoptotic necrotic cells. So we could make that the debris export rate. So that's something we might want to consider in the future. But let's fill that in here. So I'm going into my phenotype function and now checking if they're dead, doing all this. So I think we're in pretty good shape here. Let's see here, and let's continue. So now we're going to need to get the oxygen. This is a lot easier than it used to be with the dictionaries. And I just say I'm going to store a variable called O2. I'm going to get a single signal from my cell called oxygen. So it will sample the local environment at my cell's location and return the oxygen concentration, the extracellular concentration. And then I'm going to set the birth rate. So let me walk you through this code here. I'm going to get a reference value from my cell definition. So get my single base behavior for cycle entry. And then I'm going to do a linear scaling based upon the oxygen. I'm going to get my parameter values, my saturation proliferation. So it's custom : the name of my custom parameter value, and then my threshold. And then I'm going to use my built-in linear response function to say that between threshold and saturation value, I'm going to scale linearly my proliferation rate from 0 to the reference value. And then I'm going to set my behavior, so set the cycle entry for my cell to this new rate. So writing, a response function now is only a few lines of code. And hopefully you'll see that you can use a syntax over and over and over again. So it starts to become kind of a habit on how you build cell phenotype rules. And now let's do necrosis. Same thing. I'm going to get the maximum rate of necrosis from that custom parameter value that I set. And then I'm going to scale it based on a linearly decreasing function. So I'll get the two parameter values for the necrosis saturation threshold. I'm going to do a decreasing linear response function to figure out my scaled necrosis rate and then set my parameter value. So that's single behavior for my cell, necrosis rate, and the rate here. So let's set that over here. I am a little concerned that this might be case sensitive. So what I'm going to do is show you a trick. So one of these two windows, okay, this is just showing me this. So I can type make. Actually, that's not a bad idea to make sure I don't have any, at least huge errors. And I'm going to type project and pipe this into screen.txt. I'm just going to run it for a few seconds and hit cancel. Ooh, did I kill something? No, I guess I didn't. Okay, model builder's still open. That's good. I'm going to open up. This is basically the very beginning of the PhysiCell. All the screen output has been captured. This is a great way to cheat and get a list of all the signals in my environment and all the behaviors. So apoptosis and necrosis really are lowercase, so that's good news. This unfortunately is case sensitive right now, so you do want to be careful that you've matched the names. Okay, so we've got the apoptosis and necrosis set properly. And let's see here. What's next? So I've created, oops, I should probably have like a little checklist here, say that now I've declared my function, I've implemented it, and now I need to make sure I assign that function to my cell definition so that it actually uses it. So that's actually not too bad. I'm going to go to that function called create cell types. So back into, oh, that's why I closed. My code editor closed. Okay, no. Yeah.
It's John. Sorry to interrupt. It looks like Zoom is doing something odd with your screen. So
Okay.
We're seeing where your Zoom controls are. I think we're seeing a little bit of.
Oh, like a black bar that's interrupting.
Exactly. So perhaps if you just reshared, it would resolve. I'm not, I haven't seen this.
Is there some way to auto hide this? Hide subtitle? No. Hide floating meeting controls. How about that?
That resolved some of it.
Okay. Is that better?
That's better. And then it looks like to your right, is there a little box with that it has the, yeah, you're almost there, right there.
I'm
Whatever
dragging
that
your
one
window
is.
around. Let me hide the thumbnail video. Okay. Is that any better?
And then now there's only one, well, there's only one that really matters remaining, and that's, yep, you're mousing over it right now.
Oh, the
Live
closed
transfer.
captioning. That's the closed captioning, at least on my video.
Yes, that's correct.
I like closed captions. I'm hearing impaired.
Okay. Well, I think
So,
then it is minor. It didn't seem right to say nothing though.
no, I really appreciate it, John. Thank you. I'm a little irritated with Zoom that that stuff didn't disappear on its own, and I hope it's not too bad. Let's not rewind 50 minutes, though. Let's just finish the example, I think, instead.
Of course.
But, that's irritating. So we are now in Create Cell Types. You kind of scroll down, there's a little comment hint that says this is a good place to set custom functions. So let's take the code at its word, and right below this, we'll paste this stuff in. So this is that little C++ snippet that says find the definition for cancer cells, and then for cell definition functions update phenotype, we'll assign our cancer phenotype function. So we're actually just about through our example here. So now we just need to rebuild, right? We've made a new function. And now we need to recompile it so that it all gets made. And we are now in a position where we can go ahead and run. So I already set my conditions to 15, so let's not worry about that too bad. But let's go back here to the Run tab, and it should be running with the updated compile project. So click Run Simulation. Give it a second to kind of reset here. Let's go to Plot. And I think the easiest way to look is now let's see if debris is being released by dead cells. So we'll advance a few frames. I'm going to choose debris in the dropdown. No, there aren't any dead cells yet. Boy, I hope we see something die. There we go. See, a dead cell, we saw a little plume of debris until macrophages swooped in and started consuming it. So that's looking like it's working. So let's just hit play, and you can see that cells are proliferating. You should see more proliferation on the outer edges where there's more oxygen. So if I click on oxygen again, we can kind of see those conditions. And we can see that the macrophages are wandering around and co-localizing where they start seeing more debris. So it looks like we're in pretty good shape here. Let's see. So I think we're going to I want to show some more handy functions and just very quickly show you what we can do, that we can make functions to more precisely target where we place the cells at the beginning of the simulation. And so a few handy tidbits. There's a function called create cell that will return the pointer of the new cell you created. And if you pass no argument or void, you'll create a cell default. Basically, your very first cell definition, whatever has ID 0. In our case, it'd be a cancer cell. Or if you want to create cell with a cell definition passed by reference, you can do that. So you can find your cell definition and then pass it by reference and say, I want to make a bunch of cancer cells here, a bunch of fibroblasts there. And then this is really important. Remember I said yesterday, never manually write the position of the cell. Instead, use the function called assign position. And so you do my cell pointer dash assign position, and then give this, and you can set that randomly. Other things is we have a lot of built-in capabilities for random number distributions. And so there's a uniform random distribution between 0 and 1, normal distribution with a mean and a standard deviation given as applied. You can find a uniformly distributed point on the unit circle or on the unit sphere. This one in particular is important for 3D people because just picking a random angle independently uniformly would cluster too many points near the poles. So use this instead. There's also a capability to say that if I have like 5 events to choose from and I supply 5 probabilities that sum to 1, I can have this choose one of those events based upon your probabilities. That can be handy for some things. So we're going to refine our example by placing some number of tumor cells within a radius for the tumor and then some number of macrophages at a fixed distance away. So all we're going to do is going to add a few more parameters to the model. So I'm going to go back here to cell types. I'm going to click on cancer cells. or actually no, I'm going to make user parameters. I apologize here. These are more like global parameters. And I'm going to rename number of cells to number of cancer cells. So I'm going to rename this. I'm going to set it to 1,000 cancer cells initially. Go ahead and save that. I'm going to make another variable called number of macrophages. I'm going to make sure I don't have any spaces at the end, just to make sure I'm not causing troubles. This is going to be an integer parameter, so choose that from the drop-down and make 50 of those. And then I'm going to make another function called maximum cancer distance. So all cancer cells will be within this radius. And let's set the default value to 275 microns for now. And then the initial distance where we place all the macrophages, I'm going to just say that initially I'm going to put them all at 350 microns. So I've made these parameter values, and now we want to make use of them. So I'm going to edit the custom tissue function over here. So go into my code and go to setup tissue. This is what will kind of read the environment size, and then this is where it's going to go through and place the cells randomly. I'm going to comment all of this out. And I'm going to make a new couple sections here to do my own cell placement. So what I'm going to do here is I'm going to randomly place tumor cells. And so what I'm going to do is going to read my parameter value, so where should I be placing them. I'm going to find my cell definition for cancer cells, and then I'm going to go and place cells randomly. I'm going to pick a randomly uniform position within the domain. Actually, no, I'm just going to pick a random radius and a random angle, which is not completely uniformly spaced, but it's okay. And I'm going to place, write a position vector and assign that position. So let's go ahead and do that. And if I want to set other properties of my cancer cells, that'd be a good place to do it. So I could just have some heterogeneity by modifying this placement loop here. And then I'm going to place macrophages, same kind of deal. So I'm going to go through and make another loop right here, saying, find my macrophage definition, figure out how many I should be placing. So until I reach my number of macrophages, I'm going to pick a random position on the unit circle and make that my position, multiply them by the radius, and then create and place my cell there. And that is it. So I'm going to rebuild the project. So I'm just type make, and I'm going to go back to my model builder. Here it is. And then click run again. Oops, I accidentally stretched my window out. Oh well. So run simulation should clear this all out in a second. And we have just a few minutes, so I want to show you custom coloring too. So looks like we are running now. So click on plot. And now, see, it's completely, this is a little bit better, right? We have a big wad of cancer cells in the center, the macrophages in a ring outside, and I can kind of show the oxygen either fixed or not fixed, but here's the oxygen. You can kind of see that the cancer now is preferentially growing. The macrophages are definitely finding something dead and chemotaxing towards it. And so if I visualize, say, the debris, I could turn off the cells here. You can see how there's a dead clump of stuff in the center releasing debris. So we must have some central necrosis. But we haven't changed their coloring function, so we're not actually seeing these necrotic cells. We do see the macrophages kind of wandering into the center and eating things, and they're definitely getting bigger as they're eating things and absorbing their volume. So now we'd like to just improve the visualization a little bit to change the color of the necrotic cells. And so I'm going to go and, first of all, we can make custom coloring functions. Excuse me. And so the syntax of a coloring function is it needs to spit out a string of 4 colors using the W3C conventions. So RGB values or RGB alpha values or named values. Although I got to point out that the graphical model builder right now will not work for cells that don't have RGB colors. So if you say make a cell brown, like a character string, that is correct SVG format, but can't be run by the model builder right now in the visualization. So it needs to be a function that you pass a cell pointer, and then you output a string of 4 colors, the fill color for the cytoplasm, the outer outline of the cell, that color, the nuclear fill color, and the nuclear outline. And so what I find handy is to actually cheat a little bit and start formatting the output based upon a built-in coloring function. So I'm going to do paint by number, which is the default one. So I'm going to copy paste this. Oops, I probably need to do two things, right? I need to go into custom.h, and I need to declare my custom coloring function. So I'm going to just declare the function here. And then in custom.cpp, I'm going to implement it at the very end. So first I'm going to start off by paint by number coloring, and I'm going to modify those colors. So I'm going to query the cell to find out if it's dead or alive. And if it's dead, I'm going to make, if it's apoptotic, I'm going to make the cell black. And if it's necrotic, I'm going to make it kind of a coffee brown, because coffee is great. So I've made my changes here to my necrotic cells. My dead cells are now going to have a different coloring, so we can see who's who. And is there anything else? I'm going to do one more fun thing. I'm going to color my live cells based upon their proliferation rates. So I'm going to say that if my cell type is cancer, and if I'm dead, if I'm not dead, if dead is false, then I'm going to do some nice shading here. So I'm going to get the relative birth rate by saying, get my current cycle entry rate divided by my reference cycle entry rate. And I'm going to multiply it by 10 just so we can kind of expand out that range a bit. And if this value is above 1, I'm going to cap it at 1. So this will be some relative rate between 0 and 1, at least proportionally to it. And then I'm going to make my color is going to be, I'm going to basically linear interpolate between 0 and 255 based upon this current value and turn it into an integer. And then I'm going to make a character string RGB, then my RGB values. And let's see here. This says that if my color is 0, I've got 00255, which makes it a dark blue. And then as S increases, my color value increases towards 255, and it becomes 255, 2250, which will be yellow. So this will be a nice colorblind safe rendering. And then I return the output when I'm done. So I've made a coloring function, and then I need to make sure I assign that coloring function. So in the main code, so I'm going to open up main.cpp, and I'm going to assign this custom coloring function. So I look for cell coloring function, and it is defined over here. And I'm going to replace the one that was already here with my new custom coloring function. And so now I've got a new coloring. Now I've changed the code, right? So I better recompile. So hit make. And we should be, oh, it doesn't like something. Output is not declared. So let's go back to custom.cpp. Oops, standard string, but without a name. Output. There we go. Now let's type make. Now we should be good to go. So now we have done everything. This is actually a complete workthrough of the full modeling workflow. So let's go here back to run and click run simulation. Give it a second to reset over here. Looks like we're definitely running. So I'm going to go back to plot, go back to the very beginning. And now at the very beginning, time 0, all the cells are initialized to that maximum proliferation rate. So they're all a bright yellow. But now you go forward one frame, here you can really see that environment dependent phenotype. Here towards the outer edge of the tumor where they have the most oxygen, they have the greatest proliferation rate. And as you dip deeper and deeper into the center of the tumor, the oxygen is dipping lower. Notice it's below my necrotic threshold of 5. And so you can already see a few of these brown necrotic cells and then some sporadic apoptosis. So if I click on debris, we should definitely be seeing that these dead cells are releasing debris into the environment. Okay, so now we can kind of see why the macrophages are doing what they're doing. They're chemotaxing, and they're very sensitive to the presence of this dead debris, and they start phagocytosing the dead cells. You can see how they're getting humongous because they're phagocytosing cells, and they'll start co-localizing in the center of the tumor in this low oxygen necrotic region and gobbling up the materials. And then as they run out of dead debris, they're going to start wandering back into the tumor and start looking for these apoptotic bellies. So there we are. So this is a good stopping point. So we'll take a break until our next session here. But you have now seen a complete walkthrough of the entire modeling process. We start with populating the template project. We use the graphical model builder to build the environment with your, any diffusing or non-diffusing substrates in your environment. You add your cell definitions, including your custom parameter values that you need for your model. And then you declare your custom functions in your header file, implement them in C++, make sure that you assign those custom functions to your cell definitions, and you're off and running. And so from there, it's down to a matter of coming up with rules that capture our hypotheses. So thanks very much. I can take a few minutes for questions, and we'll look forward to session 7. We're going to continue this example. We're going to make the macrophage phenotype even a little bit more interesting. We had like a polarization to the macrophages, and then we'll do the zombie example when we have time. So I'm going to go ahead and stop my screen share, I think, and very happy to take questions. Let's see, I see a few in the chat window. I'm seeing a lot of crosstalk between people, actually, which is a beautiful thing. Are there any questions for me, or should we stop the recording and give people a break? So I see a question from Julio on the transformation rate. So the transformation rate would allow you to transform from one cell type to another, exactly, from type A to type B. You can do it at the code level, or you can do it in the model builder. And so I'll show an example. Actually, my zombie example will give you an example of that. And yesterday's example with the mutations will also show that you could do a few different approaches. You could make M1 macrophages and M2 macrophages two completely different cell definitions. And then you could have a transformation rate from M1 to M2. And then so if you use the intermediate workflow, then if you do the intermediate workflow, that would be a constant transition rate, that M1s would become M2s at a constant rate. But if you build a C++ function, then you can modulate that transformation rate dynamically based upon things in the environment, say pro and anti-inflammatory factors, or oxygen, or other things. Or even the cell volume might change it. Like you might have a worn out macrophage that might change to kind of a late M2 polarization, for example. So that could be modulated dynamically with the functions using these signals and behaviors. So thanks very much. And we can definitely do more of these questions during the hackathon in the next session. Yeah, if you want diffusion, yeah, so we'll leave that to the crosstalk to continue discussion in the social spaces. We'll look forward to seeing you at